Okay, go ahead.
Okay, well, before we get on to the slides about the tests, I just wanted to give a brief history. Bay Materials got into the aligner and retainer business basically in 1999. Bay Materials was a polymer chemistry consulting company aimed at solving a company's problems that relate to plastic or inventing new materials that relate to plastic. In 1999, a couple of graduate students from Stanford came to visit Bay Materials. They had a problem with the existing materials that I call commodity materials. Polyester materials available at the time were too stiff or too brittle. They cracked in the patient's mouth or not strong enough with allowing no tooth movement. So their great idea of moving teeth with plastic that they had for the Invisalign product line was having some difficulty. Bay Materials designed the first material specifically made for aligners that was a thin sheet of polyurethane and supplied Align technology for their Invisalign product line. Later, the two companies parted ways and Bay Materials launched Zendura. Zendura is our improved version of the similar product, a single layer specially formulated polyurethane polymer that is available in a thin plastic sheet. So we've been in the Zendura and Zendura dental business since 2011, and Zendura has become a popular brand. Just last year, we launched a new multi-layer material called Zendura Flex, and that material has improved properties that we'll talk about in a little bit for aligner production. Okay, and now back to the slides, and I'm going to go to share. All right, there we go.
You are good.
You thought I couldn't. You thought I couldn't do that. All right. So this slide just goes over a few of the characteristics. If you talk to clinicians or laboratories and patients about the ideal characteristics for materials, what would you build? You'd make something that had superior durability, and durability can be measured by strength or flexibility. Really, you need to have both. You can't be too strong without flexibility, otherwise the material will crack in the patient's mouth. You can't be too flexible, otherwise the material will not have enough force to move teeth. Patients require a clear product. I mean, the whole idea of clear aligner therapy is to be able to wear the product for 20 hours a day without being detected for the hours that you're out in public. And so key to that is to maintain clarity, and a lot of materials that are available stain. They might stain with coffee, they might stain with wine, with Coke. The standard test that is shown in this slide with a portion of this aligner from a popular competitive brand is exposed to a mustard. So a standardized test for staining is called the mustard stain test. And you can see what happens with some materials. Very important, there we go. So very important is elastic recovery and the ability of the material to retain its tooth moving force during the cycle of wear, which of course is hours per day, many hours per day, and also more than 1 week, and some cases more than 2 weeks. So we talked about a test for strength and flexibility. This is called the 3-point bend test, and this test, a little sample, a small sample of the sheet material is placed between 2 posts, and then a high precision force measuring device. Ours is called the Enstron brand, but the Enstron measures the force that it takes to deflect the material a fixed amount, or it deflects with a given force and measures the amount of deflection. So just depends on what test is being done. This test is done for measuring the flexural strength, the flex modulus, as well as the stress retention over a period of time. If we look at the force retention over a period of time, And in this case, we're taking materials, putting them in a 37-degree water bath. All plastic materials, when they're stressed, over a period of time decline in their ability to resist that stress, but then it levels off. So the idea is to not produce too much force when first mounted on the patient's arch, and after a day or two, retain enough force to still move teeth. So you can't cause too much pain in the beginning, and you certainly want to keep moving teeth even past a few days. If we look at advanced materials like Zendura Flex, a 3-layer material can be designed that reduces the initial force and allows patients a greater comfort level when they're first put on, but actually improve over standard materials, improve in force over a period of days, retaining more of the original force, so that over the course of therapy for a patient, we actually retain better tooth moving force. We talked about measuring the strength of material. A sample like this is cut from sheet materials. Each end is put on an Instron or other force measuring machine, and then we can measure what does it take to stretch the material, what does it take to break the material. So the tensile strength is an important test that we do. And so all these tests that I'm going over give us a comparison of materials to the ideal, or a comparison between 2 or 3 materials, so that we can choose the best properties for a material to put on the market. As I said, a lot of materials, what I call commodity polyester or PETG materials, are easily cracked. One measurement of the cracking is this test called a dart drop test. In this case, a small weight is dropped from a specific height to a sample of material below, and the deflection of the material, or its ability to withstand that impact, is measured. So some materials are better than others, and this allows us to choose Zendura polyurethane material over PETG materials. Another test of flexibility is called a tube wrap test. And in this case, we wrap a small sample of the sheet material around a tube of a specific diameter, and then expose that tube to different conditions. Maybe it's warm water, maybe Listerine, and after a period of time, take it off the tube and take a look at, is the material able to recover its shape? Is it suffering any damage from that deflection? And so you can see here, different materials also differ quite widely in the flexibility that's measured with this tube wrap test. Here's a stain test chart. Again, this is the sample of an actual aligner. A small sample is exposed to the mustard stain, but we do mustard stain tests, we test with coffee, we test with red wine, and of course those liquids are more likely in actual use to be exposed to the aligner that a patient is wearing. But the mustard test is really a standardized industrial test across different uses of plastics, and so we do the mustard test most frequently. I hope to show you that a little bit later. But again, you can see that materials vary widely. Even though they start clear, they may not stay clear. And that's an important characteristic that we want to build into materials for Bay Materials to produce in the Zendura product line. We also measure thermoformability. And you can see here, rather than use a patient's arch for the thermoforming that is so variable between patients, we use a standard shape. This is a pyramid shape that allows us to measure all 4 sides of a 4-sided pyramid with the heated material that gets flipped over from a biostar. And of course, the objective is to design a material in which all 4 sides are thermoformed equally, or with an equal amount of thinning. And this is another type of test. This is a plastic or aluminum block that has grooves of a specific diameter machined in. And what we're looking for here is very good conformance of the thermoform material to very small features in a model. And again, it helps a lot to have very predictable size grooves rather than the variables that are in a actual patient arch. All right, this is an Instron machine that is able to very precisely measure distance and force. We mount our small sample of a polymer sheet material on a 3-point bend fixture. It's a little hard to demonstrate here because it's designed to be in a water bath so that we can measure it at 37 degrees. But the concept is that a small sample of material is put across two posts, and then the third point of the 3-point bend test is the machine itself deflecting the material by pushing a rod in the middle to deflect the plastic. And that allows us to verify how flexible, how strong, how many times it can be deflected. And it also allows us to set up a longer term test. So most of those tests that I just listed are done on an immediate basis. How flexible is the material when it's first encountered? The same machine is used to measure tensile strength of the material. So a very small sample with a very specific, I don't know if you can see that, but a very specific width is punched out of a sheet so that we can compare sheet to sheet, different materials, and pull to measure tensile strength. And so the combination between flexibility and strength is exactly what we need to measure to be sure that we have a product that is going to be good for you and your patients. I'm moving our video so that we can see the second Instron here in our laboratory. This one is set up, it really is the same 3-point bend test, but controlled for a long period of time in a water bath that allows many hours or even an entire week to be measured for what the force retention is. So the material is deflected a specific amount in that 3-point bend test, usually 1 millimeter, and then the machine is going to measure the force as it changes over time. And just like the chart that I showed earlier, you can see that what's shown on this machine is the force when we deflect the material is high at the beginning and eventually decays, and it keeps on changing at a small percentage later. But the point is to design a material that is comfortable for the patient when the aligner is first put on, and still retains enough force to move teeth later, days later, as the patient wears the device. So that is a key difference in materials as we design them. Well, okay, this just shows the 3 layers of Zendura Flex. I thought we went over this, or did we? Anyway, hard on the top and bottom surfaces. The outer surfaces have a stiffer material, flexible, elastic material in the middle, and that's what produces the excellent force curve that Zendura Flex has. It's much more flexible when the patient first puts it on. It retains that force in a greater degree of its force over time as the patient wears it.
Quick question that came back. What is the I don't even know what this is, ASTM you use for the 3-point bend test?
I can provide that. I don't have it memorized.
You can email us,
yeah, sure.
Mr. Din.
Sure.
So
we do. There is a specific ASTM.
That's great. Question from Luis Paulo. He says, "Did you cut that just using scissors?" I didn't see. Yes.
I did cut. Yeah, you didn't see it because I had
we
a
were
little
talking
bit, because this model has a lot of undercuts and also we're not seeing. But anyway, I did cut it all using scissors. Because of the undercuts and the attachments, it was a little difficult to get the material off of the model but everything I did here was with scissors.
It was. I watched
It
them.
does need some more trimming, or sorry, more finishing to get rid of the sharp edges.
Any other? Did we do this one?
Oh, well, this slide just shows the enhanced view of the differences between vacuum forming and pressure forming. In vacuum forming, we only have the vacuum difference between the air pressure and the vacuum that the machine pulls on its own as pressure to do the molding. In pressure thermoforming, the pressure from above, the air pressure that's supplied above the warm material, forces the material into the mold and just does a easier job of producing a better product. And then these are a couple of vacuum formers, and those are 4 different, the BioStar on the upper left and the MiniStar on the lower left. The other 2, the ErcoPress in the middle and the Drufomat on the right, are less used in the US, but they certainly do exist. They certainly do a good job when used.